This video discusses a common implementation of the linear or sequential search algorithm. If you have not watched the video on linear search, this will be a good time to stop this video and then watch the one called linear search and then come back. If you have watched it, then you should be familiar with the steps that you see on the screen. So the linear sequential search is a basic search that says we're given a collection, and in order to determine whether or not a value that is given to us is present in the collection, we're going to inspect one value at a time in the collection, one by one, starting with the very first one, and we're going to stop as soon as we find a match or as soon as we don't have any other elements to take a look at. So the implementation is very simple. It's a method called linear search. The method has two parameters, obviously, the collection, which is called list, and key, which is the value that I'm looking for. Observation. Notice that both of these are primitive integers, and I did that for simplification. So this is an array of numbers, and I'm looking for a number. But if you change this into an object, a collection of objects, and the key is an object of the same class, it will work exactly the same. Now, the basic technique is to compare one value from this collection called list and figure out whether or not it's equal to the value that I'm looking for. This is what it does, what we do in this code. Okay, it's a simple if-else. So in the if part, we're saying, let me access one element of the array given a value of index, and then I'm going to compare that to the value that I'm looking for, which is called the key. So the bottom line is this is going to be true if there is a match, or false. If it's true, notice that I'm updating the value of found, which I'll discuss in a couple of seconds, to be true, just to indicate I found a match, I found the value that I was looking for. If I don't, what do I do? Well, if I don't, it means that this particular element is not a match. So I need to look at another element. And because this is a linear or sequential search, the element that I'm going to choose to look next is the adjacent element. So if this expression is false, there are no matches in this element, in this index, I need to go to different index. And I know that indexes in Java increment linearly, sequentially by 1. So all I have to do is to add 1 index plus plus to my current index. This will give me access to the next element in my collection. Okay? Now, what are the values of found and index, so on and so forth? Well, let me tell you a couple of things. Index should be initialized to 0. Why? Because again, in Java, the first index of any array is 0. We cannot have negative indexes in Java. So the initial value of index is 0 because this is linear or sequential search. I'm supposed to start looking at the first element in my collection. What is size? Size will tell me the numbers of elements on my collection. And I can do that by requesting Java to figure out the length of my collection. In other words, how many elements I have, and then subtracting 1. Why 1? Well, because the index of the last element, okay, the index of the last element is going to be off by 1 because we start with 0. Okay? The statement that does the comparison, determines whether or not I have a match, has to be embedded in a while loop. Why a while loop? Because I don't know exactly how many times I'm going to have to go through the collection until I found a value. I don't know where the value is, so I don't know if the value is going to be in the second element, in the 100th element, or in the 1000th element. So typically we use a while loop. Now the while loop, notice that it has two conditions joined by an and. It has a condition that says not found and a condition that says index less than or equal to size. Now the important thing to realize is that because of the and, these two conditions must be true at the same time and all times for the while loop to iterate. If one of the two conditions is false, the loop will stop. So, found, I'm going to use to stop the loop. It's exactly what we do in real life. When you find your wallet that you have lost, you don't keep looking. You say, oh, I found it, and then you stop. So as soon as there is a match, as soon as we have an item, an element in the array that matches our key, we need to stop. That's why we set found to true. Because of this, we need to initialize found to false. Before we start looking, we don't know whether or not there is a match. We don't know if the value of key is part of my collection list. Therefore, it makes sense to assume that founds will be false. So let's analyze the condition. If found is false, when the computer evaluates this, it's going to say negation of false. The negation of false is true. And that's exactly what we want. But once we found a match, we want then found to be true. So the next time that this is evaluated, it's going to be evaluated as the negation of true. The negation of true happens to be false. This expression will be false, and therefore this entire condition will be false and the loop will stop. That's precisely what we want. We want the loop to stop. We want to stop searching as soon as we found a match. What about the second condition, index less than or equal than size? Well, as in real life, you look in different places, you don't find what you're looking for. At one point, you're going to stop looking around. At one point, you give up. You say, it's lost, I don't know where it is. In terms of what we're doing here, what that means is you're giving a collection and you're giving a value. And after inspecting every single element in the collection, you conclude that none of them matches what we are looking for. So this statement is never true. It's always false, which means all we're doing is incrementing the indexes, traversing our collection sequentially one by one, and at the end, we need to say stop because there is nowhere else to look. We inspected every element, there are no matches. So I'm going to create this condition that says, let me compare the value of the index that I'm currently using, and let me make sure that the index value is less than the size of my collection. Okay? So what happens when index is greater than the size of the collection? Then this condition will be false. And again, because that condition is false, this whole condition will be false and the loop stops. That's precisely what we want. So let me repeat. We want this condition to be false as soon as we found a match or after we inspected all the elements in our collection. Okay? Either condition will make the while loop stop. Now, after this loop is executed, because we have those two conditions, we don't know which of the two was the cause that made the loop stop. We don't know, in other words, whether we found a match or we inspected the entire collection and there are no matches. So we need this if-else to differentiate between the two cases. So notice that again, I'm using the Boolean flag found. And found at this point is going to be either true or false. It will be true if I found a match, false if I didn't. At any rate, computer is going to evaluate found and it's going to say, well, if found is true, then I know that there is a match. Okay, I know that this statement was true, and then I know that there is a match located at this index. Therefore, all I need to do is to return the current value of index. But if found is false, which means I never found what I'm looking for, then I should indicate that. But I need to return an index, okay? So what value of index do I return? In programming, it's commonly used a -1 to return a value to indicate not found, okay? Why -1? Well, because we're talking about Java, we're talking about collections. Collections most of them have an index, but indexes cannot be negative. So when you search for something and the result of that search is a negative value, that should indicate to the rest of the program not found. This is why the type of this method is not Boolean, as most people would expect. Most people will expect this to be true or false, saying, yes, the element is found, the element was not found. But if you think about it, this is not very useful. If it's found, where is it? You want to perhaps modify it. Maybe you want to delete it. Maybe you want to print it out. So to do all those operations, you need to know the exact location. In other words, you need to know the index of the value that is a match. So returning a Boolean is not very useful. Thus, we return an integer. We return the index of the element that contains the match, or we return a value that is so absurd that so illogical that will indicate to us that is not a match. And typically that value is -1. So somewhere else in the program, we will need to analyze what the value of the integer is. Is something that we expect, which is 0 or positive, or is something that will indicate to us that the value is not found, which is -1. So this is a very basic algorithm. So to end this video, let me repeat the analysis that we saw before. So remember, a linear or sequential search, we compare values one by one in sequential order, starting with the first one. And this is very simple because we're talking about arrays, which has indexes, and we can move from one index to the other. This probably and most likely, as in real life, requires a lot of time, a large numbers of comparison because we are comparing one by one. So again, imagine a very large collection, 10,000 elements, 250,000 elements. So we're going to require a lot of comparisons. So we said that the expected running time is proportional to the size of the collection. N represents the numbers of elements. So the larger the value of N is, the larger numbers of elements we have in the collection, the longer it's going to take to either find a match or to go through the entire collection and conclude that there are no matches. So again, if you have not watched the video that discusses linear search, then you should do so and then come back to this algorithm.